Today we are going to talk about shear center, which is an extension of the theory on shear flow distribution or shear stress distribution in thin walled beam due to a shear force. So we will first talk about shear center of thin walled open cross section beam, and next move to shear center of thin walled but closed cross section beam. So please keep in mind the concepts that we are going to talk about is valid for open cross section beam, okay, and not yet for closed cross section beam. So let us first move into the definition of shear center. So what is meant by shear center? Okay, so if I have a thin walled cross section beam, there is a point on the plane of the cross section through which if the shear force passes through this point, then the torsion because of the shear force is going to be 0. Okay, so let me just repeat what I said. So shear center is the point through which the shear load should act to produce no twisting or no torsional moment in the cross section. Okay, let me write it down. Shear center is the point through which the shear forces or shear loads should pass or should act so that to produce no twisting or torsional moment of the cross section. So let me try to explain it physically. So let me have a cross section which is completely asymmetric. Okay, there is no symmetry in the cross section. A generic, I mean, of course for symmetric cross section also there is a shear center, but let me just take a generic thin walled cross section. So to make it generalized, we are assuming that there is no symmetry in the cross section. Now there is going to be a point, so this is the x-axis, say this is the x-axis of the cross section, this is the y-axis of the cross section. Say this length is 2a, this length is a, this length is b. Okay, and let x and y be the centroidal axis, c being the centroid. So somewhere, okay, there would be a point somewhere here, okay, or somewhere, sorry, so there would be a point somewhere on the plane of the cross section, that is on the xy plane, anywhere over the xy plane. So this is the point which is called the shear center, such that if Sy and Sx, that is the applied shear forces, passes through the shear center, then these forces are not going to create any twisting of the cross section. Okay, so if the shear forces do not pass through the shear center, then the shear forces are going to produce a twisting moment, right? So now it is obvious that if I have two forces Sy and Sx in the plane of the cross section, it's obvious, right? It is very intuitive that they are going to produce a twisting of the cross section, right? So this Sy and Sx is going to produce a moment or torsional moment about the z axis. So both Sy and Sx will produce a torsional moment about the z axis, which is the lengthwise axis of the beam. Okay, now our point is that it is obvious, right? If I have Sy and Sx in the cross section plane of the beam, then of course it's going, both Sy and Sx is going to produce a moment about the z axis, and this moment is the torsional moment. So because of the torsional moment, there is bound to be a twisting of the cross section. But our point is that if Sy and Sx passes through a particular point which is called the shear center of the cross section, then there is going to be no twisting of the cross section. So how is this possible? This is possible because the moment produced about z axis by Sy and Xx will be perfectly balanced by the internal shear stress distribution in the cross section or the internal shear flow. Shear stress of course is going to produce shear flow. So the internal moment produced by the shear stress distribution is going to perfectly cancel out the torsional moment produced by Sy and Sx. So there is going to be no resultant torsional moment or resultant twisting of the cross section. Okay, so this is the overall idea behind shear center of a cross section. Now the question is that why are we trying to find out the shear center? So you will see that we will spend a considerable time in finding out the shear center of a cross section. So you will see it is much more easier for a open cross section beam, and it's quite difficult to, quite cumbersome to find it for a closed cross section beam. So why are we taking all this pain to find out the shear center? This is for two reasons. One is that any shear load, suppose I have a set of shear load which is say Sy dash and Sx dash, which is not passing. So Sy dash and Sx dash are not passing through the shear center. Or not acting at the shear center, whichever way you want to call it. Okay. Okay, so now the idea is that if we in reality it is not necessary that the shear forces acting on the beam is going to pass through the shear center. Okay, but then we have to analyze the beam for any such shear stresses acting on the beam. So what do? What we do is that we replace Sy dash and Sx dash by a corresponding set of shear stress passing through the shear center plus the torsional moment of Sy dash and Sx dash about the shear center. So what we are going to do, the equivalent of Sy dash and Sx dash is that we will take this here, it is going to be Sy dash and Sx dash, plus we will consider a torsional moment. Okay, this is going to be empty due to Sx dash and Sy dash about the shear center. Okay, so that is going to be my, so once it comes at Sx and Sy, right? That is going to be the first step. So the next step is that once I do find out this equivalence set, which will consist of sy dash and sx dash and the torsional moment mt, I will analyze the shear flow in the cross section first for sy dash and sx dash. Okay, keep it aside, then again find out the shear flow in the cross section because of mt, and then I am going to use the superposition theorem and add up superpose the two sets of shear flow, and that is going to give me the actual shear flow in the cross section. Okay, so suppose for sx dash and sy dash, so for sy dash and sx dash through shear center, I am going to get a shear flow qs in the cross section, and for mt I am going to get a shear flow qt in the cross section. So the actual shear flow is going to be q, which is going to be qs plus qt. Okay, so that is the reason why we need to find out the shear flow shear center for a given cross section. Okay, so let me just summarize whatever we have discussed and put it in words. The thing is that any shear load can be represented by shear load through the shear center and a torque. So the first point is that any shear force can be represented by shear force through the shear center and a torque. Okay, so that is the first point. The second point is that the stresses produced by the separate action of torsion and shear force can be added. Stresses or shear flow, whichever way you want to call it, okay. So once we formulate the equivalent system, then we find out the shear stresses or the shear flow for individually for the shear stresses and the torsion, and then add them up by using superposition theorem. Okay, and the third point about shear stress is that for a symmetric cross section, shear center lies on the axis of symmetry. For a symmetric cross section, singly or doubly, Okay, so this is the theory behind the shear center. Now we will solve an example and see how the shear center can be evaluated for a open thin wall cross section. So let me just clear the can. Okay, so let us take up an example which is going to solve the problem. Okay, so let me take a cross section, a C cross section. Okay, so so this length be H, this length be B, this length be B, and say this is the x-axis, this is going to be the y-axis, this is the centroid. Uniform thickness T. Okay, so let me say that the shear center okay, now let us look into this problem. So this problem is singly symmetric. Okay, so this is a singly symmetric cross section. Okay, so it is symmetric about x-axis. Therefore the shear center is going to lie on the x-axis. Right, so now what I need to do is to find out the other coordinate. Okay, so it is not symmetric about the y-axis, so shear center is not going to lie about the y-axis, so it will be somewhere off from the y-axis. So let us consider that the shear center is at a distance, okay, zeta from the outer edge of the C section. Okay, so and to find out this zeta I have to consider Sy, that is acting on the cross section. So and since so only Sy is going to suffice and Sx and be considered to be 0, because I don't need to find out the location of the x coordinate of the y coordinate of the shear center. So I can take Sx to be 0. Now this is done. So let me now see how can we find out the shear center. Okay, now what is going to happen? Because of this applied shear force, there is going to be a shear stress distribution in the cross section. Okay, and this shear stress distribution is going to be Qs. Can be represented by the shear flow Qs, where I know that Qs minus Q0 is going to be that huge equation, right? If you remember that equation, it is going to be, let me just, okay, so that huge equation that we had, Qs minus Q0 is going to be minus Sx into Ixx minus Sy into Ixy by Ixx Iyy minus Ixy square 0 to s dx ds plus, okay, that big expression that we have. So once I know Sx and Sy, I can find out Qs in the cross section, okay, along the cross section. Now what is going to happen? So we can choose any point on the cross section or on in the plane of the cross section, and the moment produced by the applied force Sy in this case should be equal to the moment about the same point by the shear flow Qs. So let me just put that into another in other words. So we have to choose any point on the cross section, on the plane of the cross section. So let me call this as A, let us say, okay. So so what has to happen if Sy is passing through the shear center, then the moment produced by Sy about A should be equal to the moment produced by Qs about A. Okay, so A could be any point on the cross section, right? So only then we can say that there is not going to be any twisting of the cross section. There is not going to be any resultant torsional moment left, and there is going to be no twisting of the cross section. Now it is our job to choose this A wisely or smartly, so that the calculation that we need to do is minimized, right? I can see in principle I can choose any A. So I have to just find out the moment produced by Sy about A. I have to find out the moment produced by Qs about A. Okay, but to minimize my work, the work need to be done in calculating this moment, I should choose A smartly. Now how am I going to choose A smartly? I have to see where to choose my A. That will vary from cross section to cross section. The motivation remains the same. The motivation is the minimum calculation to be done to find out the moment about that point. That's the motivation. But depending on this motivation, we have to use our understanding of the cross section and choose the point. Like for this particular cross section, I will choose the point to be here. I will choose this to be my point A, because about A, the contribution to the moment because of this Qs is going to be 0. The contribution due to this Qs is going to be 0. So the only contribution to the moment at A is because of this leg. Okay, so let me number the points. So let me call this as 1. Sorry. Let me call this as 1, this as 2, this as 3, this as 4. I mean, let me erase off the 8. Okay, now let us see. If I choose point 3, then the moment about 3, so moment about 3 will be due to only Q12. Okay, the other shear flow are not going to contribute to the moment, because they all moment at 3, because they all passes through 3. Okay, so therefore to find out the shear center, if I choose point 3 as the point about which we are calculating the moment. I just need to find out Q12. That's my only job. Okay, now let us try to find out Q12. So what is the first step in finding out the shear flow Q12? First step is sectional property. Okay, so sectional property Ixy is equal to 0 because it is symmetric. Okay, and Ixx is going to be h cube t by 12. I am not going into the steps for calculating it because it is pretty straightforward. H cube t by 12 1 plus 6b by h. Okay, I would not need Iyy. Okay, Iyy will not be needed because Qs minus Q0 is going to be minus Sy Iyy by Ixx into Iyy into dy ds 0 to s. So this is going to cancel out, so I will have minus Sy by Ixx into 0 to s dy ds. Okay, so that is the only expression that is required. So I don't need to calculate Iyy. This is another trick. I mean, when you have to find out the shear flow or the normal stress because of applied bending moment, first check which sectional property you need before going ahead and finding out all the sectional property. Okay, so now Q0 is going to be Q1, which is equal to 0 because it is a free edge. Okay, therefore so this is going to be for flange 1 2. So for flange 1 2, okay, or portion 1 2, so Q12 is going to be minus Sy into t. T is not a function of x, so I can take that out. Ixx into y ds 0 to s. Now what is that? What is y for portion 1 to 2? So I have minus Sy t by Ixx. What is going to be y? Y is going to be minus h by 2. So I have h by 2 into s because y is going to be minus h by 2 for flange 1 2. Right? So I have this to be of this form. Okay, now this is done. So now let me erase this off. So now I know Q12. Okay, so let me carry on the, so Ixx is going to be equal to h cube t by 12 6 1 plus 6b by h. And Q12 is equal to Sy t h by 2 Ixx into s. Now let us try to find out moment at point 3 due to Q12. So that moment is going to be what? So Q12 is the shear flow. So that is shear stress into thickness. So the force is going to be Q12, which is a function of S, we know. Q12 S into ds is the force, okay, because it is Newton. Q12 is Newton per meter into ds is going to give us Newton. So this is the force, right? And that into the distance from point 3 is h, okay, and that I need to integrate between 0 to p, right? So it is going to be q1 to s into ds into h. So if I write down that, I have sy th square by 2ixx 0 to b s ds. So which is sy th square by 4ixx into s square 0 to p, which is sy th square b square by 4ixx. Okay, so this is the moment produced by the internal shear flow. Therefore, moment produced by okay, so moment at 3 due to sy is going to be sy into zeta, okay, and that therefore this is equal to this, so that the torsional moment is 0, the net torsional moment is 0. So I have sy into zeta is going to be sy into t h square b square by 4ixx. So sy cancels out, so that gives me zeta is equal to b square h square t by 4ixx. So if I write this down, so this is going to be, if I put the value of ixx, this zeta is going to be, this is going to be 3b square by h 1 plus 6b by h. This is my answer. This is the answer. Okay, so done. Right, so this is how I find out the shear center for a thin wall cross section open. Okay, closed one is little more intricate, which we will talk about later. So I will solve some more problems which will be posted soon, but I wish to say that in Maxon chapter 8.2 there are several problems both on pure bidirectional bending, the shear flow due to shear forces, and also the problems on finding out shear center. The answer keys are also given, so it is a good book to do practice problems for understanding the concepts. So thank you.